Not on fire!
That probably works better if the piece of metal you're trying to heat up doesn't have glue on the end of it for some reason. This is an induction heater. It uses high frequency and high current to make a magnetic field that can heat up metal objects. This one can be bought on Banggood for about $5, runs on 12 volts, and has a coil big enough to heat up some screws. So I rigged up one of these cheap 12 volt power supply units from, either eBay or Amazon, and I made it into a 12 volt power supply to power this thing. But this coil size is only about a ½ inch diameter, which means I can't melt anything very big. This bad boy, on the other hand, has a much larger coil and can heat up something a lot bigger. This larger induction heater can take anything from about 12 to 48 volts, but the higher the voltage, the more power it's going to be able to put out. He did! So here I have a 48 volt power supply that says it can deliver 20 amps, which comes out to about 960 watts. So that should be plenty for this induction heater. So in this video, I'm going to be making an enclosure for this power supply that'll make it much safer, and we'll have some current and voltage measurements. Now, since this is a cheap eBay power supply, we're going to also be testing in this video whether it works in the first place and if it can actually deliver the current and voltage that it says it can. We're already off to a bad start here as the warranty sticker is already ripped. And right out of the box we have a couple of bent tabs. This piece is also bent. But I like a challenge, so let's get started. Let's run over the basics of my old 12 volt power supply. I just kind of jerry-rigged together this plastic box that I had lying around. I just cut a hole in the back so it would fit. But the main component that I want is to have this feature right here, and that's a switch. This takes the 120 volt input. You've got a switch, it's also got a fuse, and then we're going to have some sort of power output here. So I've got a 120 volt inlet, fuse, and switch, and for its output, I'm just going to be using a wall plug. Now these power supplies can't go from 0 to 20 amps instantly, so you got to have a switch on the DC to give these a kickstart. MOSFETs here have to alternate, and if you don't give it the full 20 amps immediately, they're both going to go open at the same time and it's just going to be a short circuit. So to mitigate that, I'm going to put this big switch into the DC output. We've also got a voltmeter and ammeter that can go up to 50 amps with this current shunt right here. And of course we've got a big old 25 amp inline fuse. And since the warranty label already came ripped, I guess I got nothing to lose by taking it apart. So over on the input side of it, we've got some over voltage protection, a varistor, 2 of them actually, a bunch of capacitors, we got like a choke. Here's the full bridge rectifier that converts it back to DC. These are the smoothing capacitors for the full bridge rectifier. I just noticed something very wrong right here. If you notice, the switch is in the 220 volt position instead of the 110. Now I'm not sure exactly what would have happened if I plugged it in while it was on the 220 volt instead of the 110. I assume it would just have less power, but yeah, it's a good thing that sticker was cut. Otherwise I would have never opened this and found to switch it back to the 110 volt. Alright, now that it's switched back to 110, I'll put it back together. I'm going to be making the enclosure out of 1/2 inch MDF like this. So I'll take some measurements and draw up a plan. I'm going to be cutting the pieces of MDF out with a cordless circular saw, but instead of using the standard general purpose blade, which has 16 teeth, I'm going to be using this 140 tooth blade, which is meant for cutting plywoods, MDF, other things like that. The more teeth is going to give a sharper and crisper cut. Let's fix these bent tabs. Well, so here's the general shape of her, and you may notice that there is a lot of extra space inside, and that was intentional, and that's because these induction heaters require cooling. It's going to require a fan to go on top of the board to cool these big old MOSFETs right here, even more than the heat sinks do, and it also needs liquid water running through this coil. So I don't have the components right now, but I've made extra space inside this enclosure so that I can put a small water pump and the voltage converters to step down to 12 volts probably for the cooling fan. And eventually I also want to put a variable step down voltage regulator so that I can basically have a lab bench power supply and the induction heater power supply all in one. So the power supply's got a cooling fan on the back here, so I'm just going to take a hole saw and cut out a hole for that fan so it can breathe. Perfect.
Oh, it's beautiful.
Now I'm going to drill a hole for the connector. Yep.
Yep.
Now this shaft for the on-off switch isn't long enough to make it through the 1/2 inch of MDF. So I'm going to have to make it so it sits a little bit lower. So I'm going to router it out. Apparently the hole for this switch is 29/64. They just couldn't make it something easy like 1/2 inch. Well, it's not pretty, but it goes on the inside and it gets the job done.
They ask you how you are, and you just have to say that you're fine when you're not really fine, but you just can't get into it because they would never.
No one's ever gonna see that. Well, I was gonna cut out the hole for the ammeter with the jigsaw, but I can't find my blades, so I'm gonna have to go the old-fashioned way. Alright, the X-Acto knife's taking way too long, hence Plan C.
No.
Why didn't I think of this earlier? Now I'm gonna do the same thing for the power outlet. To attach all the pieces at right angles, I'm going to be using the Craig pocket hole jig and some 1-inch screws because that's the right length for 1/2-inch wood. Most people might find it difficult to screw in pocket holes on the inside of something, but I've found a way to cheat. Yep, right angle adapter.
He's the one. Like a boss.
Oh yes, I keep the bank rolling.
Like a boss.
Sipping lean, big paper hold it.
Like a boss.
You know we got it locked now.
Like a boss.
Bailey coupe with the top jam.
Nice.
Nice.
And here it is assembled. So I've poked holes with an awl everywhere I want to place the center of each screw. Now that I've got the cover off, this should be pretty easy. So to figure out how I'm going to wire up the new power switch, I'm going to take apart my old power supply and do it the same way. So it looks like I'm going to connect the ground terminal to the ground on the power supply, which is this one over here. The neutral goes to the neutral in on the power supply, which is this one right here. Then the live wire is just connected directly, which goes to this fuse, and then this fuse gets connected to the switch, and then the switch goes to the live of the power supply. So the wiring for these cheap Chinese Hong Kong long schlong ammeters is a bit difficult. For some reason, you can't measure the current and the voltage of the same source, otherwise it'll burn them up. So now let's see how to wire it without burning them up. These thick black and red wires over here are the current sensing ones. This small red wire here is the voltage positive of the measuring. The yellow wire is the voltage sense wire. and the black is ground of the voltage. I'll draw the schematic real quick, and then I'll come back and explain what each part is. Over here we have our 48 volt power supply. We've got the positive and the negative. The positive is going to go through to our switch, then to our fuse, which goes through our load, which is in series with the current shunt. That then goes back to the minus of the power supply. Now for the sensing wires, we've got the positive and the minus, or the black and the red wires for the current sensing wire across the shunt here, so it can detect the current, and that's a 75 millivolt shunt. And then the tricky part is for the voltage sensing. We have the voltage positive and our sense wire connected to the positive of the power supply, and then our ground is not connected to anything. So what that's going to do is it's still going to use the regular ground, and it's going to show us our voltage still without burning out our ammeter. I've just dropped the other screw for the other terminal, and I can't find it anywhere. Someone's coming to watch me work. Since I lost the other screw, this new one's going in whether it likes it or not. That's how you thread a new hole. Now let's trim it down to length. Screw heads aren't big enough to hold the wires, I'm using 2 washers to sandwich it. So I'm going to plug it in and make sure the power supply at least powers on. And while it's apart, I'm going to be wearing these gloves just to make sure I don't get shocked. And we've got power, as indicated by the green light. The ammeter, however, is not turning on. Okay, as you can see on the meter, it is reading 48.3 volts. I think that's pretty good, and I'll assemble the box now. Now here it is all assembled. Now I can give it a paint job later, but for now let's test it out. I've scratched a plus and a minus into the plug so I know which one's which, but I'll paint one side to make sure that side goes up when I plug it in. Now plug it in and see if the induction heater works, and I'll only run it for a short period of time because it's going to get pretty hot without any cooling. And And we'll test it by heating up the end of this wrench. Okay, it appears it's shutting off because it's drawing too much current. Now, just touching the wrench a little bit, it is actually pretty hot. Too hot to touch completely for any longer than a short period of time. The coil itself is a little warm. The MOSFETs are totally fine. In the beginning of the video, I showed the small induction heater heating up this screw, so let's try that again with the bigger one. Okay, it's holding steady at 48 volts, and I'm reading that off the voltmeter this time because the one that's built in is not working for whatever reason. Now I'll stick the screw in. Alright, it's smoking a little bit, and it's red hot. The coil itself is very hot, so I'm going to submerge it in some water this time. Without proper cooling, the coil is going to get so hot that it's going to conduct the heat back and melt these capacitors here, so we don't want that. Now I've submerged the coil partially in water. Hopefully that will keep it a bit cooler. Steel rod. If I back out a little bit, it comes back. Move in a little slowly. And the steel has changed color on that side. Now let's submerge it in the water. Yep, I think it's hot. So the power supply mainly works, except it just cuts out under high load. And that can mean a couple of things. One, either the power supply can't put out the current that it says it can, or the wiring in there is not up to spec and this wiring is just too thin to handle that much current. Either way, I had a great time building this and testing out the induction heater finally. That's just been sitting here for such a long time. I finally got to use it and heat some stuff up. It was cool. That's it for this video. Subscribe for more content like this, and I'll see you guys next time.